Hey, how's everybody doing today? Welcome back to the Math for Healthcare video lecture series. We're in the exponential functions section, and today's lecture is solving exponential functions, part 1. And in order to get to part 2, we're also going to have to look at logarithmic functions. We should be able to get to that today in this lecture, and then the next one will be how to use logarithmic functions to solve the exponential equations. What do I mean by solving the exponential equations? Well, if you recall, we had this problem last video. We had suppose a bank account compounds continuously at 3% annually. You deposit $2,500 into the account. How long does it take for the balance in your account to reach $10,000? Recall that we set up the equation. Well, first of all, as I want to say is note that, remember, modeling this, the equation is A of t equals 2,500 e to the 0.03. Well, I'll make it a function of x, okay, just to match the slide here. Oops. Function of x is equal to 0.03x, okay, and remember we use that letter e to represent Euler's number when it's continuous compounding, and that's 2.71, blah, yada, yada, yada. It goes on forever. If you want to look at all those digits, feel free to go ahead and look it up on the internet. For us, all that matters is we know it's a special number that never ends, never repeats, and it's about 2.71. All right, now, however, this question didn't ask us for the balance after 5 years or 10 years, but it asked us when does it actually reach 10,000? So we set up this equation. Well, we want to know when the total is 10,000 equal to 2,500 e to the 0.03x. Now, if you recall, we did I divided both sides by 2,500, but then we got stuck because of this variable up in the exponent. We don't really know how to deal with that yet. So, solving exponential equations, part 1, it's a basic way to solve exponential equations. Also helps us understand them. But I'll be honest, it's not going to help with this one. Specifically for this one, we are going to need the logarithmic functions, so we will introduce them in the second half of this video. All right, so one strategy is based on the fact a to the x equals a to the y equal if and only if x equals y. All right, so what does that mean? That means something like this. Let's see, how can we interpret that? Notice, okay, so let's say we have 2 to the x equals 2 cubed, right? Remember, 2 cubed is 8, just to remind us. So that means, what does that mean? Let me just erase that, just to remind you that equals 8. But 2 cubed equal to 3, that means, so x has to equal 3 in that case, all right? So if you can massage the bases to match, you can solve the exponential equation, all right? For instance, in this example, we have 2 to the 3x plus 4 equal 2 to the 7th. What does that mean? That means, thus, 3x plus 4 equals 7. Okay, and now we could subtract 4 from both sides, so 3x equals 3. And finally we see, so x must equal 1. All right, good. Now let's look at a couple more here. Okay, solve square root of 5 to the negative x equals 5 to the x plus 3. All right, so here we need to use the fact that square root of 5 is equal to 5 to the 1/2. Okay, so we have, let's think about this. We have 5 to the 1/2, all raised to the negative x. What do we do with exponents? We multiply them. So this is equal to 5 to the negative x over 2. And on the other hand of our equation, this is equal to 5 to the x plus 3. So now we're in the same base. And so using our principle from before, we know that negative x over 2 equals x plus 3. Right? And now we solve for x. Let's say we add x to both sides. That leaves me with positive x over 2, right? Because 1x minus x over, negative 3x over 2, because we subtract x from both sides. Negative 1x minus x over 2 is equal to negative 3/2 x, and that must equal 3. Finally, we multiply by our reciprocal, and so x equals 3 times negative 2/3, which is equal to negative, negative 2. Right. A little more complicated. The square root one is a little reminder. Square root of 5 equals 5 to the 1/2. Now, just to get that out of my way, how about this next one? Okay, so we got 1 over 27x. Let's think about that a second. So 1 over 27 all raised to the x. What's 1 over 27? That's equal to 27 to the negative 1 all raised to the x. And we could rewrite this as 27 to the negative x. Okay, and this is equal to, using this equation here, this must be equal to 81 to the x plus 7/4. All right. Now, these look like different bases, but in fact, these are base 3, and you could always check that. But so 27 is 9 times 3, right? But 9 is 3 times 3, so we get, so 27, actually I'm going to do this in a different color. We have 27 equals 3 cubed, and why don't you try this on your own? 81 with the base 3 is equal to 3 to what? Pause it, think about it. Okay, and that's equal to 3 to the 4th. All right, so now let's see what we have. We have 3 cubed, all raised to the negative x. Okay, equals 3 to the 4th. I'm just substituting and rewriting 81 and 27 in there in a different way. Okay, raised to, we got to multiply, so we end up with 3 to the negative 3x equals 3 to the, don't forget to distribute that 4 when you multiply, so it's 4x plus 7. 4 times x plus 4 times 7/4. Now we have negative 3x equals 4x plus 7. Subtract 4 from both sides, we get negative 7. Subtract negative 4x from both sides. We get negative 7x equals 7, so x equals negative 1. Oh, so I lost that last little bit there. X equals, since negative 7x equals 7, x equals negative 1. Okay, and you can check that works out for you. So that's nice and all, but it's not really what we want, because we still can't solve this equation, even if we divided both sides by 2500 first. Okay, we get 4 equal e to the 0.03x. We can't write 4 in base e. Okay, generally for solving applied problems, you're not going to be able to manipulate the bases to be the same. All right, so what we need here is our logarithmic functions. All right, so let's see what they are and what they have to do with things. things. All right, so our main tools for solving exponential are going to be the logarithm functions. Mathematically, logarithms are the inverses of exponentials. What do I mean by that? It means that whatever exponential does to a number, a logarithm undoes to a number. In other words, basically, let me see, log, let's say, just pick a base 2 of 2 to the third, that equals 3, right? Let's think about it. What is the function 2 to the x do to 3? It raises it to the third. That's this guy. And so the log undoes that. Right? That's the idea of inverses. Another way to see that is what's called the exponential form of logarithm. Okay. First, so we need a greater than 0. Remember, we wanted our bases to be greater than 0. X is any number, and it's our independent variable. Generally speaking, is y equals a to the x, the exponential function. That means that log base a of y equals x. Okay. Now, before we go there, let's look at this example real quick. So let's look here and write the exponential form, which is sitting right here. How does it come to that? Log base 2 of 8 equals 3. All right. Oh, that's actually what we saw up here, notice. So what is that really? How I read the logarithm itself is, okay, what's the answer over here? 3 is what I raised 2 to in order to get 8. Which is a little confusing, I know. So a better way to think about it is, what do I mean? Okay, the exponential form is your base 2 raised to the right side 3 equals 8. And that is in fact exactly what this is saying, and we see that matches up over here. Now there's two main bases classically available on calculators. The logarithm base e is called the natural logarithm and is denoted ln of x. That's pretty much the only one I use for solving exponential equations. And we'll see how we could do that even if it's not in the same base. And y equals natural log of x if and only if e to the y equals x. Same thing there. So what I'm saying is, let's say I have, so the natural log of e to the x returns x, right? And then there's also base 10, and that's usually spelled out log. With no base written, that's a 10. And that's useful for some applications, but generally I don't use it to solve any equations. You can, but there's the reason this is the natural logarithm over here. But again, what is that base is really 10 here when it's not written. So 10, the base 10 raised to the y equals my argument x. All right. Let's see how that works a little bit more. So a little practice in going between exponential form and logarithmic form. All right. We want to rewrite the following as logarithmic expressions. Remember here, what's the base is 10, so we got log. I'm going to explicitly write it out because it's 10. You don't necessarily have to write it there. Log base 10 of 100 equals 2. Right? What do I raise 10 to get 100? It's 2. That's the answer. So, one thing to think about is logarithms are kind of like getting at the exponent. They're going to, in some ways, that's how they act, and it's good sometimes because when you have really small or really big numbers, you just don't want to deal with these huge numbers and exponents, and we could take a log and reduce things. Okay, this next one we have, what's the base? 100. So that says log base 100 of 10 equals 1/2. Lastly, still have a base. Now we have a base of 10. we say log base 10 of 1 over 100 equals negative 2. Right? Now, how about the other way? Okay, we could solve these. One thing's, let's say we're searching for this number over here, right? X. We want to know what that value is. We could put it in the exponential form if we have a tough time thinking about that, what x is. And that says, and this is good practice of what logarithms mean. It means 4 raised to the x, 4 raised to, remember 4 raised to what number gives me 64. And we get that, let's see here, what is that? 4 to the, I believe it's 4 to the, oh, I'm just going to double check here what I got in my Desmos. 4 to the third. Sorry about that. Well, I'm not always the quickest with my calculations. Sometimes I got it. Okay, now, oh, this is a big number, but let's change colors. The exponential form of this equation is 7. Let's say we're searching for the side x. 7 raised to what number equals 343. Okay, we're just going to try some out. I don't know my 7 powers. Let's say 7 to the third. Oh, look at that, right under money. So x is equal to, 3 again. I promise, they're not always all 3. Okay, log base 1.5. So what do I raise 1/2 to get 4? This is a little tricky. And I think it's worth writing down the exponential form again. This is our x, and so this is 1/2 raised to what power equals 4. Okay. Oh, well, we need it. 2 squared is 4, but this is 1/2, so this is going to be x equal to negative 2. Hopefully we can see that. Right, because 1/2 raised to the negative 2 is equal to 2 squared, which is equal to 4. And lastly, I'll leave the last one for you to do on your own here and try that out. Oh, actually, that's a little tricky. Let me see here. I'll do it. You convinced me. Do x here, and we get 2 to the x equals 3/2. That is a pain in the butt. We're not going to worry about solving that one, what the number is. So there's some logs that are reasonable to evaluate yourself, others that aren't. If this was a different base, then so the base e and the base 10 we could plug into our calculator to solve. Let me do one example of that, I think, before I move on. Another example is, let's say I have ln of 3. What does that equal? Well, by the way, what do we know? It should be a little bit more than 1. No, let's pick it, because we're asking what power do I raise e to get 3, right? And notice over here I have my function in there. I could just check, okay, ln of 3. Okay, so that's about 1.099, say. Okay. And so you can see we can just calculate these when we have the correct bases, and natural log is the easiest to use for that. All right. I think that what I'm going to do is I'm actually going to cut this video here, and I'll record another video tomorrow that talks a little bit more about logarithmic functions and then how to solve exponential functions using those logarithms. And we'll start with these identities here. All right, have a great day.